Development Pharmaceuticals in association with Higher Secondary Principals Forum.
Namaskar. Hello viewers. Today I am going to speak about physics. What exactly I mean by physics? What do you study in physics? Physics is a study of natural occurring phenomena. What exactly I mean by this natural occurring phenomena? How to describe this natural occurring phenomena in terms of physical quantities? Find the correlation between these physical quantities, measure these physical quantities, and that is what is physics is all about. Now, what exactly I mean by this? You have a simple situation in 11th standard syllabus. Object falling from certain height. What are the parameters involved? What are the physical quantities involved? First of all, height, speed, acceleration, gravitational force. These are the parameters. You describe all the parameters involved in natural occurring phenomena, and then you understand physics behind that. You find a correlation between these quantities, measure these quantities. Similar situations you have in 11th standard, covered in various branches of physics. Another example I can say, when you heat a conductor, in thermal properties of matter you must have studied. If you heat a conductor, conductor expands. To what extent it expands? That's a natural occurring phenomenon. So some phenomena you study in different branches of physics in 11th standard, and some branches of physics you study in 12th standard. Now, for example, another natural occurring phenomena which you know, you pass a current through a conductor, the magnetic field is produced surrounding the conductor. So this is a natural occurring phenomena. Optics, you study so many phenomena. Now, this phenomena are covered in this type of phenomena are covered in different branches of physics. So let me tell you about the 12th standard syllabus as such, and then we'll straight away start a topic in this 12th standard itself. So the first two chapters covered under branch of physics called electrostatic. Electrostatic deals about charges at rest. Then you have third chapter called current electricity, and in this chapter you study what is called charges, everything about charges in motion. What is meant by current, what is meant by resistance, what is meant by resistivity, all that you study, and the measurements about this you study in current electricity. In these three chapters, that is chapter 1, chapter 2, chapter 3 are there for your formative, and one more chapter which is there which is called as electromagnetic waves. The fourth chapter which you study is moving charges and magnet, where the current is sent, what exactly is the effect surrounding that conductor, that you study under magnetism, and you will get the answer to the magnetic property. Why any material act like a magnet? Why any material show a magnetic property? Why rubber is not magnetic whereas the iron is magnetic? That you are going to study in this particular part of chapter. Then you have what is called as electromagnetic induction, totally different chapter, but opposite to that, the concept which you do in moving charges and magnetism. So you change the magnetic field surrounding the conductor, and you have a current induced in the conductor, that you study in the electromagnetic induction chapter, and the applications goes to transformer, building up of a transformer. Michael Faraday is the discoverer of that particular concept. Then you have electromagnetic waves, where electric field and magnetic field interaction is explained. Interaction is explained, and you understand the propagation of electromagnetic waves. Then this is the part 1 of physics of 12th standard. In part 2, the first chapter you study is about ray optics and optical instrument. Ray optics, you study the light traveling in a straight line. Sometimes light do bend. Sometimes you do only the ray optics approximation, and when the light bends, when the light casts a shadow, it spreads in the shadow. All that you learn in wave optics, where you encounter the situation where light travels in the form of wave and explains that propagation of light, Christian eigen theory. Then you have a dual nature of the chapter called dual nature of light, where you study the light travel sometimes behaves like a wave, sometimes as in a quantum nature. That quantum nature of light is explained. The next two chapters of nuclear physics, atoms and nuclei, structure of atom, what exactly is there in the atom, various theory presented, that you are going to study. And nuclei, you are going to study how exactly the nucleus, different nuclei behave, what is meant by radioactivity, how one can understand nuclear reactor. That more or less, the gist of that is done in nuclei. Semiconductor physics and the communication, last two chapters is the modern physics. Semiconductor, you study about diode, transistor, applications of that, and communication system, you study about different terminology involved in communication system, FM, PM, and so frequency modulation, wave propagation. This is more or less the 12th standard syllabus. So let's start. We have to do the first chapter first today of the 11th. So fasten your seatbelt and get ready to study the first chapter of chapter 1 of 12th standard. What exactly it deals about is electric charges, electric charge, force and field. So you are going to study what is meant by electric charge, what is force and what is field. Let me tell you the content of the chapter. It's nice to learn first the content of the chapter and then you take one by one concept at a time. I'll tell you about the main concept involved in this chapter also. So what exactly you are going to study in this chapter is first part you are going to study about electric charge. How this electric charge idea is created more or less. The historical background, we can go in detail of that. Then you study the force around the force between the charges, the space around the charges, different assembly of charges, how exactly they produce the field. This is the content of the chapter. Concept called electric flux and its application that will help you to find out electric field due to various charge assemblies. Now, what is meant by charge assembly is the question mark. What is meant by charge is a question mark. So let's try to go in deeper of this particular concept. So let's focus on first the electric charge. Now, electric charge, if you understand, if you must have, in younger days, you must have played with the various type of experiment. In lower standard, you are very curious to do science experiment, though that curiosity becomes less and less at the later stage. But initial stages at 7, 8, 9 standard, you try to do experiment. Whatever is performed in the class, you try to do it at home also. So you must have tried taking a plastic comb and then bits of paper. You take this plastic comb near bits of paper, you will find nothing, no attraction. But if you rub this plastic comb and then you take it near the bits of paper, then bits of paper attracts. Similar type of situation you can also try with the help of a straw. You take a straw, charge this straw and take it near the bits of paper. You will find the bits of paper will attract. Similar assembly I have here. If I rub this straw and take it near this, then this straw will develop a charge and it will try to repel. So situations, this type of situation you must have tried. Now let's pose some question and then we'll move forward. First of all, when you take a charge comb near the bits of paper, why does it attracts? Second question, if you take a metal spoon and charge it and take it near the bits of paper, you won't be able to attract bits of paper. And third thing, if you take a metal spoon and if you wear insulated gloves in your hand and take it near the bits of paper, you will be able to attract some bits of paper in that case. So let's try to see whether we can get the answer to these three questions going through the first part of the topic. So the first part of the topic is frictional electricity. So what exactly is this frictional electricity? Electricity developed due to rubbing. So what exactly happens when the body is rubbed, when the object is rubbed? These type of experiments were tried in ancient time as well. Thales of Miletus in 600th century BC, they have mention of this type of experiment where they took a glass rod rubbed with silk and another glass rod rubbed with silk. They found that two glass rods repel each other. If you take glass rod rubbed with silk and ebonite rod, amber or ebonite is some type of resin which you rub with fur and try to take it near close, it will attract. So they try to categorize, there are two types of thing which is existing now. And William Gilbert, the philosopher William Gilbert, who was working for Queen Elizabeth I, he tried to categorize this. And the clear categorization was given by Benjamin Franklin, who said there should be two types of charges in nature, positive charge and the negative charge. So body which is rubbed loses charge, loses electron and acquire positive charge, and body which gains electron acquires a negative charge. The concept of charging came into existence. Okay? So charging means loss or gain of electron. Body loses electron, it acquires positive charge. Body gains electron, it acquires negative charge. Now there are various methods of charging. One of such method is by charging by contact, which I have depicted in this particular first diagram, where you take a charged body and uncharged body. If you touch uncharged body to a charged body, the charge gets distributed, and after some time, if you take it apart, you will find that both the bodies will have equal amount of charge, provided they have same dimension. And that particular method of charging is called as charging by contact. The second method, which is called as charging by induction. In that method, near to the neutral sphere, if you take a negatively charged body, positive charges will induce nearer surface, negative charges will induce further away surface, and if you try to connect the other surface to the ground, all the electron will flow to the ground, and we can get what is called as positively charged body. That is the way of doing positively charged body. Now this connection to the ground, that is called as grounding or earthing, and it helps the charges to flow to earth. Likewise, one can create a negatively charged. You bring a positively charged here, body here, negative charges will induce, without touching the body it will get induced, and here there will be a positive charge, and ultimately if you connect this other end to the earth, electrons from the earth flow to the body and it will neutralize that side of the body, and you will get what is called as negatively charged. So one can get positively charged body as well as make a positively charged body as well as a negatively charged body. Now three questions which I had posed. Let's try to see whether we got the answer to these three questions. First I said, what happens when the charged comb is taken near bits of paper? Which method of charging comes into play here? And you will find that method of charging is nothing but the charging by induction. So when I take a charged comb near the bits of paper, not touching the bits of paper, the opposite nature charges develop on the paper and the paper attracts. But you will wonder to see one more thing. When the paper particle touches the comb, it quickly repels because it gets negative charge, similar charge that of the comb, and it repels. Same way, the second question which was there, you take a metal spoon in your hand and then you try to take it near the bits of paper. You won't able to attract because your body is a good conductor. And all charge which you develop because of the rubbing will be lost through your body, and that's the reason you won't able to attract bits of paper. And suppose, and the answer to the third question, if you try to take an insulated gauze in your hand and take a metal spoon and take it near bits of paper, to some extent you will able to attract bits of paper. So you will get the answer to all these three questions in the first part of the chapter itself. And from this, the role of grounding or role of earthing is very important. Any any institution, any infrastructure, any building, if you see, there should be a good earthing, because amount of charge, if excess of charge is there, that has to leak to the ground. Otherwise, that will damage all the television set or the refrigerator, this type of devices which you have in your houses. So earthing or grounding plays a very major role. So this is the first part of the topic, where you do what is mean by charge, the methods of charging, two methods of charging, what is mean by frictional electricity. That's the first part of the chapter. Next thing, we'll study what are the properties of this charge. So we know what is meant by charging. When the body loses electron, it acquires charge, that is positive charge. When body gains electron, it acquires a negative charge. So let's try to understand what are the properties of charge. The first property of charge you should know is quantization of charge. What is meant by quantization of charge? Quantization of charge means charge is made up of smaller things. We can express a charge in terms of integer times smallest charge. There will be a smallest charge which we call as fundamental charge, and we write that fundamental charge as E, and it has a value 1.6 into 10 raised to minus 19 Coulomb. This is the smallest charge we have. We cannot have a smaller than this charge. This is the smallest charge. And the charge on any extended body is expressed in terms of this smaller charge, plus or minus NE, where n is the integer. This integer means it could be 1 times E. If 1 electron is lost, it will be 1 time E. The charge acquired body will be 1 time E. If 2 electrons are lost, the body will acquire charge of plus 2E, where E is the smallest charge. If somebody tells you that there is a charge existing 1.4 into 10 raised to minus 19 Coulomb, don't believe in that, it is wrong. The smallest charge is 1.6 into 10 raised to minus 19 Coulomb. Then, this is the idea which is called as quantization of charge. You can think total charge is integer times the smaller charge. We cannot have a charge 0.5 into E. This is not possible. Then, the second property is additive nature of charge. Charge is additive in nature. One body I can imagine made up of many smaller charges. So charge is additive in nature. That you do under the property called additive nature of charge. Then, conservation of charge. What is meant by conservation of charge? Charge is conserved. Total charge of the system is conserved. For example, if you take a glass rod and the silk system, when I rub a glass rod with the silk, the charges are just transferred from the glass rod to the silk cloth, and it is just transferred, and it is not created as such, neither destroyed as such. So this is called as law of conservation of charge. So we say charge is conserved. Let's take the example of this. Now suppose we have a charge body. A is the charge body, and I have an uncharged body B. Both have same dimension, and if they are touched now, the charging by contact, A and B, and they are separated, they will acquire half of the charge each. So total charge before and total charge after remains same. If that charged body Q by 2, if I touch to another uncharged body C, you will get two bodies B and C charged respectively as Q by 4 and Q by 4. So charge before and charge after remain same. Similar type of expression you can understand also. Suppose in radioactivity, neutron goes out. When neutron is given out, it gives a proton. Proton plus the electron is ejected, plus some uncharged, some particle is emitted along with that electron. This type of reaction you are going to study in nuclei chapter number 13, which carries just 2 marks. So neutron goes out to make a proton, electron, and this particle. I can find the charge of this particle using law of conservation of charge. Neutron is neutral, proton is positive, electron is negative. This is neutral, no charge this side. Before interaction, after interaction, proton gets a positive charge, electron negative charge. This is neutral. That means this charge should be also neutral. So this particle which is called as antineutrino is an uncharged particle. So law of conservation of charge will help you to understand this part. So this is what is called as law of conservation of charge. Then you should know what is the difference between the charge. This is an interesting thing to know. What is the difference between the charge and mass? The first difference between charge and mass, charge could be positive, charge could be negative. Mass is always positive. Charge is independent of speed. Mass increases with the speed. That's what it also means. Charge is non-relativistic, where mass is relativistic. Then charge is quantized. Mass is, whether it is quantized, it has not been established. Charge is strictly conserved, as I spoken just now. And conversion of mass to energy, you know by famous equation, Einstein equation, E is equal to mc square. Then every charged body possesses mass, but every massive body may not carry charge as such. For example, neutron, it has mass, but it don't have any charge as such. And we also say what is called as specific charge. This is not there mentioned in the syllabus as such, but you should know what is meant by the charge to mass ratio that help in discovering the electron. And it is very important, J.J. Thomson experiment, he discovered charge to mass ratio. Go through that experiment and see how was the electron discovered. So that's a further physics if you want to go through, though it is not there in the syllabus. As a curious physics student, you should go read about it, and you have plenty of internet input. Go through that and try to find out. This is about the difference between the charge and the mass. So we know what is meant by charge, what is meant by smallest charge, what is the formula for a total charge on the body plus or minus NE. One can solve many numerical based on this. Interesting thing I will tell you. What exactly mean by 1 coulomb of charge? How many electrons will make 1 coulomb of charge? That we can do by using this particular formula. And if you try to find out this, you will get N as 6.25 into 10 raised to 18 electrons. So about 10 raised to 18 electron constitute 1 coulomb of charge. Now if you want to try out some different situation, suppose this is a body, this loses electron at the rate of 10 raised to 9 per second. If loses electron at the rate of 10 raised to 9 per second, what is the charge acquired by body? First of all, since it loses electron, it will acquire positive charge. How many electrons are lost? 10 raised to 9. So what is the charge acquired in 1 second? I can find out. So in 1 second, the charge acquired will be plus 10 raised to 9 into 6 into E 1.6 into 10 raised to minus 19. One can find out this as 1.6 into 10 raised to 10 minus 10. This is the charge acquired in 1 second. You can likewise try to find out what is the charge acquired by a body A in 1 hour, 1 year, and you will love to understand, you will love to go to this particular part, and you will just resort to one beautiful thing. It will take about 198 years to build up a charge of 1 coulomb, which is very interesting. So 1 coulomb of charge is a large amount of charge. It will take almost 200 years to build up a charge of 1 coulomb when you lose an electron. That body loses electron at 10 raised to 9 per second. So physics has to be studied in terms of magnitude. If you try to understand magnitudes well, you will love to understand physics as well. So this is what exactly mean by 1 coulomb of charge. 1 coulomb of charge is very large amount of charge. Now next thing what we are going to study is forces between the charges. And the forces between the charges is given by a famous law called Coulomb's law. And what exactly that Coulomb's law state? It is just similar to the Newton's law of gravitation which you studied in 11th standard. So what does exactly the Coulomb's force law state? If there are two charges Q1 and Q2, then the force of attraction or repulsion is directly proportional to the product of the two charges and inversely proportional to the square of the distance between the two charges. So if there are 2 point charges, then the force is directly proportional to the product of the magnitude of the two charges and inversely proportional to the square of distance between the two charges. And if you put this, then you will have the relation F is equal to Q proportional to Q1 Q2 upon R square, and if you put equal to sign, the constant comes into play. That constant K is 1 upon 4 pi epsilon 0 Q1 Q2 upon R square. Now this epsilon 0 is very interesting term. If the two charges are placed in vacuum or a free space, then this epsilon 0 which comes into play is called as permittivity of free space. And if you place this particular two charges in the medium, then formula turns out to be 1 upon 4 pi epsilon 0 Q1 Q2 1 upon 4 pi epsilon Q1 Q2 upon R square, where epsilon is called as permittivity of the medium. Okay, and you have a constant, dielectric constant, medium. This quantity is related to the medium, which is epsilon upon epsilon 0, which is called as medium characteristic quantity, that is dielectric constant. So that's what exactly is the Coulomb's law. This Coulomb's law you can express in terms of vector form also, and in vector form you have to take vectors into account, the unit vectors into account, that you can more or less put it up and see. Now let's try to understand what are the characteristics of Coulomb force. First of all, this particular formula of Coulomb force valid for point charges. Then also it is valid for symmetrical charge distribution. Second important point which you should understand is Coulomb force is a central force. Now what is meant by this central force? This is very important characteristic of Coulomb force, which will help you to draw diagram and solve numerical if you understand this particular point. What is meant by central force? If this is a charge Q1, this is a charge Q2, the Coulomb force always acts along the line joining the two charges. This is always acts along. You cannot have a force this way, unless there is a third charge in the vicinity. If there are two unlike charges, if this is Q1 and this is minus Q2, then it will act along the tool, along the line joining. That is what meant by central force. It could be attractive or repulsive. Conservative force, the electrical force is a conservative force. The work done in this particular, with the help of this particular electric field using a charge, moving a charge, it is independent of path travel, and it depends on initial and the final position that you have done in the 11th standard. What is meant by conservative force? It follows inverse square law. That is very interesting. As you take a charge apart, the electrical force decreases. Then you have they obey principle of superposition of forces. You can find out the force on one charge due to many charge. Now for example, force on this charge due to this charge, I can write as force on charge 1 due to 2. Likewise, I can write force on this charge 2 due to 1. This is the way to understand in terms of vector form. So if you want to understand the force between many charge, then assembly of charge, then net force you can find out due to one charge, another charge, third charge, and so on. If there are many charge in the vicinity, one can find out the net force acting on this charge. Now this point is very important. This part is very important because you should know to solve numerical based on this. And the last important point is stronger than the gravitational force. Electrical force is stronger than the gravitational force. You can take a simple example of two electrons, and one can compare electrical force and gravitational force. So this is one electron, this is another electron. You take a mass of the electron. Mass of the electron is 9.1 into 10 raised to minus 31 kg. Charge of the electron is 1.6 into 10 raised to minus 19 Coulomb. Coulomb is the unit of charge. And if you use this fact, you find the electrical force, you find the gravitational force, and compare, you will find electrical force is much stronger than the gravitational force. So using this concept, you can understand the forces between the charges. So this more or less gives you the idea to solve numerical based on these forces. So if the situation comes, if there are many situations which are based on this part, for example, if the charges are at the corners of the square, you can find out what is the interaction between this. What will be the net force on the charge in this? If there are charges at the corners of the square, if there are charges at the corners of the triangle, if there are charges placed at the different points, and you want to find out the interaction, then you can use this principle of superposition of forces and try to find out the force acting on one charge due to another charge. After studying the electrical force between the two charges, understanding forces between the charges, let's try to understand what is the space around the charge. You know, in this room, if you consider the space around you, wherever you are, the space around you is the gravitational field. How can one can test that field? You just drop an object from certain height. If it is falling down, that means there is a gravitational field present. If I have a bar magnet, and if I want to find out that bar magnet is producing enough magnetic field, how I can test that there is a magnetic field? I can place any other carbon ion containing material. If it attracts, then we'll say that magnetic field is present there. If I place a magnetic needle at that particular point, if it deflects, we'll say that magnetic field is present. If you place a bar magnet over there, and that bar magnet experiences some attractive or repulsive force, then we say that magnetic field is present there. So likewise, if I want to define electric field, is a space around the charge. The space around the charge is called as electric field. And if I want to find out the field near this charge, then if this is a charge, and this charge is Q, which is called as source charge, and if I want to find electric field at this point P, then place a test charge at this point, and then find out what is the force test charge you place at this point, what is the force of attraction or repulsion. If it is positive, then repulsion, and then electric field will be just approximately equal to force upon charge. Now question arises, why it is approximately? Now it all depends on what is the magnitude of test charge you are taking. If you take a test charge large enough, you won't able to get the field produced only by the source charge. I want to get field produced by the source charge at this particular point. So how to get that field due to the source charge? You place this test charge as small as possible. So that's the reason in this formula we take limit of Q tending to 0. The charge should be very, very small, and then only we will able to find electric field at this point due to this source charge. This electric field has a unit Newton per Coulomb, and one can write this in vector form as well. So limit of tending to 0, F bar upon Q, where Q should be very, very small. Now, using this, one can find units of this Newton per Coulomb. I can find out dimensions of this. Dimensions of the Newton I can write. Dimensions Coulomb you have to write in terms of ampere. And then you can find out dimensions of this quantity also. Now, what is exactly meant by field due to a point charge? How much is the field due to a point charge? E is equal to F by Q is a general formula, approximately general formula to find out the electric field. But if you want to find out electric field due to a point charge, then you take a point charge, express its position vector. This is suppose a point charge. If I want to find out electric field at this point, say C, taking another test charge, say Q, express its position vector, and then this is suppose a vector which is joining charge Q and small q, then R bar you can take as R2 bar minus R1 bar. You express this in terms of vector, and you will able to find out electric field as 1 upon 4 pi epsilon 0 q upon r square r cap, where r cap is nothing but the unit vector along this r bar. And how to find out this unit vector is r bar upon magnitude of r bar. So this formula which gives the electric field due to the point charge, this is the point charge. And if you want to write it in scalar form, this electric field is nothing but 1 upon 4 pi epsilon 0 q upon r square. This is a magnitude of the electric field intensity due to the point charge, and its direction will be depending on the electric force they experience. If it is repulsive, this particular charge will experience repulsive force at that point. In that direction, field will act, and that we'll discuss more in the later part of the chapter. Then one can get also electric field relation in terms of electric force by using Coulomb's law. F is equal to 1 upon 4 pi epsilon 0 q1 q2 upon r square. Now, if you take this part is nothing but 1 upon 4 pi epsilon 0 q upon r square is nothing but electric field due to charge q1 and into charge q2. So what does it mean? So if there is an electric field in this region, and if you place a charge q2 in that region, E bar is the electric field in this region, q2 is the charge placed in that region, then q2 will experience a force. This charge q2 will experience a force in the direction of the field, and that force is electric field due to q1. q1 is somewhere here, suppose. Okay? And then you can easily understand the relation between force, electric field, and the charge. So electric field is equal to force upon charge. Force is equal to charge into electric field. So generally, we can use this formula, force is equal to charge into electric field. Then this particular electric field, then you can understand in terms of lines of force. Now, what is meant by these lines of force? Let's try to understand that part. So lines of force is the concept which helps in defining the electric field, in understanding the electric field, how one can understand electric field and depict it on a paper efficiently using this lines of force concept. This line of force concept or streamline you must have studied in the 11th standard under viscosity chapters, streamlines, properties of streamline, similar type of concept we have to use here. And let's try to understand what is meant by this electric field lines. So when I say electric field lines means line, it's a line or it's a curve. If it is a curve, then tangent to that will give the direction of electric field. If it is a straight line, then tangent to that direction is the electric field itself. So line could be curved or a straight line. Now, for example, if you want to express uniform field in a region, uniform field means intensity at any point is same. If I have intensity 10 Newton per Coulomb, at any point in that particular space, 10 Newton per Coulomb, it is a uniform field. So uniform field we represent parallel equidistant line. This is what we do, we represent uniform field. This is a uniform field. Okay. Now, if you have the point charge, so this is the way how to represent uniform field. This is what exactly meant by line of force, and the tangent to the line of force gives the direction of electric field. Now, what are the properties of lines of force? That is very interesting. So the first property of lines of force is they never cross it. It is just like a streamlines, my dear student. Two streamlines never crosses each other. So lines of force never crosses each other. If they cross each other at the point of intersection, there will be two different directions of electric field. So two streamlines never crosses. Two lines of force never crosses. They never crosses. If they cross, then at the point of intersection, there will be two different directions of electric field, which is not possible. Then, streamline from the positive charge goes away from the positive charge. We can draw streamline away from the positive charge. Streamline due to negative charge terminating on the negative charge. Then we have a streamline pattern due to positive charge and the negative charge. Streamline pattern due to two equal charges, positive charges. Beautiful representation of that you can see. And then you have, if the two charges are similar but of different magnitude, then the streamlines are slightly different. One can find out that there will be some neutral point in between where, for example, for this here, there will be a neutral point at the middle, at the midpoint. There you can find out the neutral point between the two like charges, and that point the electric field will be zero, electric force will be zero. So this is what exactly mean by the electric field lines and its properties. We have studied lines of force pattern, two equal charges. If there are there, then the lines of force pattern, if you observe at particular point, you will find no line passing, and that particular point where the electric field is zero or force is zero. One can ask number of numerical based on this, where you have two charges, Q1, Q2, positive. Both the charges are positive, separated by a distance r. And if you want to find out the neutral point, at some point there will be a neutral point. If these two charges are of different magnitude, and some point there is a neutral point, then this distance you assume as x, and I can find out this distance x. Shortcut formula you can arrive at, and the formula will be root of q1 into r upon root of q1 plus root of q2. This is a direct formula which will help you to find out at what distance from the charge q1 you will able to find that electric field or the force acting at this point is zero, electric field is zero. That is called as neutral point. Now this is the case when the two charges are similar charges. If there are similar and opposite nature charge plus q1 minus q2, now you will never find electric field will be zero in this particular region. It will be either this side or either this side. So this will be, suppose distance x2 you take, this distance you take x1 at which the neutral point is observed. Here electric field is zero, at this point electric field is zero, and distance between the two charges is suppose r. One can easily find out this x1 as root of q1 into r upon root of q1 minus root of q2. And likewise, I can find out neutral point x2 from charge q2 as root of q2 times r upon root of q1 minus root of q2. These are the simple formulas, direct formulas to be employed to solve numericals. So if you want to have an edge in any competitive exam, you should resort to a very quick formulas which you will able to use and solve that particular situation as fast as possible. This was the situation where you have two different charges, different like charges, unlike charges. But if you have two equal and opposite charge, that assembly we call it as a dipole. So we call that as an electric dipole. So what is electric dipole? Electric dipole is the assembly of two charges, equal and opposite charges, separated by a distance. So if the distance is a and the two charges are plus q and minus q, then we have that particular combination is called as electric dipole. This line is called as axis of the dipole, and the perpendicular line bisecting the two will be called as equatorial line. So there are two lines, axial line and perpendicular, which is a bisector line. Now, this electric dipole moment is a quantity associated with the electric dipole, and that quantity is nothing but P is equal to Q times A, where Q is the magnitude of each charge and A is the separation between the two charges. And you can write this in vector form, P bar is equal to Q times A bar. So if you try to understand different situation based on this and try to find out dipoles movement involved in that, let me give a simple example where suppose I have a triangle, equilateral triangle, and there are 3 charges here. So this is suppose a plus 2q charge. This is suppose minus q charge. This is minus q charge. In this assembly of charge, I have about 2 dipoles. I said dipole moment is always from negative charge to positive charge. So this minus q and one among this positive charge will form one dipole moment. This particular charge and one of the charge, half of the charge of this will form another dipole moment, and one can find net dipole moment, total dipole moment by using law of parallelogram of vectors, and the total dipole moment or net dipole moment one can write as P1 square plus P2 square plus 2P1 P2 cos theta. So this is the formula which is involved by using law of parallelogram of vectors. So in this case there are 2 dipoles in the assembly. Likewise I can have 4 dipoles in the assembly. So where we can have 4 dipoles, more dipoles in the assembly. Suppose this is a square, and if there is a plus 3q here minus q, here minus q, here minus q, how many dipoles I can figure out in this particular diagram? So due to minus q and one of this q, there will be one dipole. Due to this minus q and one of the q, another dipole. Due to this minus q and one of this, you'll be a third dipole. Find out the net dipole moment based on this, if this distance is given as A. So it will be a beautiful situation to find out net dipole. These are the numericals which we can solve. So this is about electric dipole moment. Next, we learn what is meant by electric field on the axis of the dipole. What is meant by electric field on the axis of the dipole? So how one can find out electric field on the axis of the dipole? So here we have a diagram. So you have to take an interaction of 2 charges. We have a plus q charge, minus q charge. This is the axial line. At point C, we have to find out the electric field, and you choose a distance from the center of the dipole to that particular C as r, and then you try to express what exactly is the contribution of electric field due to plus q charge, what is the contribution of minus q charge at C. Contribution of plus q charge at C is E plus bar. It is in that direction, because if this is a plus q charge and this is a point, the electric field due to this particular charge at this point will be in this direction. Electric field due to minus q charge at this point will be in this direction, because lines of force are directed away from positive charge. Lines of force are directed towards the positive charge. That gives the direction of electric field. And net electric field will be direction in the stronger field direction, and that is along E plus bar. So if you try to find out E plus, which is 1 upon 4 pi epsilon 0 q upon distance square, some distance square, distance from the charge is bc square. Likewise, you can find out the distance electric field due to minus q charge, and then you find out electric field due to 2 charges. Add up, substitute, and you will get the final relation for that. And the final relation is nothing but E on the axis is 1 upon 4 pi epsilon 0 2 pi r square minus a square square. And if you take a dipole short, very, very short, then electric field will be 1 upon 4 pi epsilon 0 2 pi upon r cube. So you take this distance very, very small, you can neglect this a square, and you can easily find out the electric field due to a short dipole, that is on axis of the dipole. Then we have what is called as electric field on the perpendicular bisector of the dipole, where you choose a point on the perpendicular bisector. Then contribution due to plus q charge at this point you draw, that is E plus bar. Contribution due to negative charge at this point is along this, because it is a negative charge, and draw a parallelogram to get the net field due to these 2 charges. And then if you try to resolve this E plus bar and E minus bar into its components, you will get E plus cos theta, not bar, that's a mistake, E minus cos theta, there E plus sin theta and E minus sin theta. Those components will cancel each other. This type of resolution of vector you have done in 11th standard, and you will get the net field because of this E plus cos theta, E minus cos theta. Substitute this, practice this, and you can resort to this final answer. And for short dipole again, you take this distance very small, electric field on perpendicular bisector, you will get as 1 upon 4 pi epsilon 0 P upon R cube, where P is the dipole moment. Now this derivations you have to try. Step by step you have to go. Once you learn the concept, it's very easy. And the connecting equation you should know. What is meant by derivation? Derivation one can derive very easily, understand very easily, study very easily if you know to draw the diagram first, describe what is there in the diagram, express whatever is there in the diagram, word it, then you see what is the connecting equation, rehearse it in your mind, and you will be able to produce a derivation very easily. So always I say derivation is like a song. You start singing it and you will be able to get it, but you have to rehearse it in your mind. The next concept which is there is if you place a dipole in external field. Now suppose this is a dipole. So this is a plus q charge and minus q charge. I can say this is a dipole. And now if I place this dipole in the electric field, what exactly happens? This plus q charge exert a force in a direction of the field, minus q charge exert a force in opposite direction of the field, and it will try to rotate. This is the rotation of the dipole. This is what exactly meant by rotation of the dipole, torque acting on the dipole, which will make the dipole to align in the direction of the field. And if you want to find out that torque acting, you just use a definition of torque, perpendicular distance into magnitude of force acting on each charge. And then you will get a simple formula, P is sin theta, where P is the dipole moment, E is the electric field, theta is the angle this particular dipole makes with the direction of the field, and you will get this particular formula. So torque acting on a dipole you can understand, and hence you can understand various things when you place a dipole in electric field, what exactly happens, how much is the torque, if it is rotated in a magnetic electric field, what happens, and if it is rotated opposite to that of the field, then it acquires a potential energy that you study in chapter 2. So in this chapter till now we have done different concepts, electric charge, electric force, electric field, what is meant by electric dipole. We have learned assemblies, single charge, dipole, multiple charges. Then we have discussed what is called as electric lines of force. Now we'll carry on with the concept of electric lines of force, depicting the electric field in terms of lines of force. The concept which you are going to learn is electric flux. What exactly meant by electric flux? Now suppose this is particular torch I have. You imagine this is a charged body. This is a charged body and it is emanating electric field in this direction. If it is a positive charge, electric field lines emanates from this particular body in all the direction. Now if I hold this particular element having fixed area in my hand, and if I impine a light on this as if electric field is falling on this particular, you cannot see the electric field, but only the animation of that we can do. So here I am depicting a light coming out from the torch as if it is an electric field. Now if I hold this element very close, then the lines of force passing through this element will be more. As you can see, the light intensity falling on the surface is more. So similar way, electric field will be stronger at this particular point. So lines of force passing through this particular surface will be more. If I hold the same element of same area at far distance, you will find electric lines of force going through this surface will be less. So it depends on first electric field intensity. So the first factor on which electric flux depends is electric flux depends is electric field intensity. Second, now if I change the area of this, if I make it half, then lines of force passing through this will be half number. So it depends on area. You can take S or you can take as A as the area. And pay attention to this part now, very interesting. Now if I try to move this element, rotate this element, you will able to see the number of lines of force or the intensity of light falling on that surface changes. So as you rotate, it goes on changing. What does this means? That means electric flux is depending on the intensity of light, depending on the surface area, and depending on the orientation of the element with respect to the surface. So if I want to find out the flux through this particular surface, then, and if it is falling normally on the surface, if the lines of force are falling normally on the surface, what I can do is I can take a small element of the surface. So you take a small element of the surface. The procedure is very simple, and you find out the flux through this small element. So if I consider small element of this surface, I can take flux through this element, and that flux through this element is denoted as d pi. Small flux through that small element is E ds cos theta. And if you want to find out the flux through the whole surface, now whole surface here will be the area of the surface itself, which is length into breadth here. If I take a circular surface, then it will be pi r square. So depending on the surface, if it is a three-dimensional surface, then it will be surface area of that particular surface. And if you want to find out total flux, then total flux, you can do this, integrate this, you will get total electric flux to the surface. So this procedure you have to adopt to find the electric flux through the surface. And this area, the flux through this element is changing, and this particular area we call as an area vector. We never treat a vector area as a vector. Charge, time, mass are the scalar quantity. Area, volume, density are the scalar quantity. But this particular area we treat it as a vector because its magnitude matters and its orientation matters with respect to the field. So flux through this matters if its area changes and orientation changes. And that's what area vector. We take conventionally the direction of this area vector always normal to the surface. So normal to the surface is the area vector, and we denote that area vector as ds bar, and hence one can write this flux as dot product of electric field and the area vector. So this is the concept of area vector you should know. One can use this particular procedure to find out electric flux due to different assembly of charges. If I have a point charge, here, and you take if you want to find out the flux through this particular surface around the charge, then you take a small area of the surface. Area vector you mention, positive charge will have an electric field in that particular direction away from the charge, and use that formula to get what is the flux through the sphere around a charge. Likewise, I can do it for a cylinder if it is placed in an electric field. Electric field, you can take three surfaces of the cylinders, you can take A, B, C. Contribution from each surface you can take. Contribution from the curved surface will be 0 because electric field and the element vector are perpendicular to each other, and one can resort to show that total flux through this closed cylinder is 0. Then we have a very interesting relation which gives you the relation between the flux and the charge. This is an easy way of finding the total electric flux through a surface. One can find out using a Gauss's law. What does this Gauss's law? So if you want to find out the flux through a closed surface, suppose this is a charge and you want to find out the flux through a closed surface, then flux through this closed surface is directly proportional to charge enclosed. And if you put equal to sign here, it is 1 upon epsilon 0 times the charge enclosed, and epsilon 0 gives a value of 9 into 10 raised to minus 12 Coulomb square upon Newton meter square. This value you can find out earlier using 1 upon 4 pi epsilon 0 k value, and this epsilon 0 we can substitute to give the flux. Now this flux is nothing but the number of lines of force. So if the charge is stronger, it will emanate more lines of force. If charge is less stronger, it will emanate less lines of force. Now, depending on the system involved, you can construct a surface around this charge which is called as Gaussian surface. And this Gaussian surface, the shape will help you to find out the total electric flux, and it will help you to do some applications of this. Let's go through the application part of this particular Gauss's law. The first application which you should know in this particular chapter is the electric field due to line of charge. So suppose we have a line of charge. This is an infinite line of charge, and you want to find out electric field at some distance r. Then you can find the electric field at some distance r using this concept of Gauss's law. So just take the surface element ds bar, curved surface, contribution for an electric flux due to this surface and phase will be 0 because ds bar and electric field are perpendicular to each other. Here you have a small element vector in the direction of the electric field, so theta will be 0. If you see the contribution from this, electric field, total electric flux will be equal to E into E ds cos theta actually it is, and it will be E into 2 pi RL. Theta is 0, and that is the contribution due to the flux through this curved surface. Now, what is the charge enclosed by the surface? Since this is a line of charge will have linear charge density. This is called as linear charge density, charge upon length. This charge upon length is called as linear charge density. So charge enclosed in this particular length of the wire, we can take as lambda L. And if you use a Gauss's theorem, what is that Gauss's theorem? Flux upon is equal to 1 upon epsilon 0 charge enclosed. You can easily resort to the formula E is equal to lambda upon 2 pi epsilon 0 r. So using the concept of Gauss's theorem, one can understand how to find out the electric field due to line of charge. Similarly, one can find out one can know how to find out electric field due to a infinite sheet of charge. Infinite sheet of charge, you have surface charge density. So you have to mention what is called as surface charge density. The surface charge density is nothing but sigma is equal to Q upon A or Q upon S. You can use this particular formula to find out the relation for electric field intensity. So here we construct a Gaussian cylinder. Since we cannot enclose a whole surface, infinite sheet of charge inside a surface, so we construct a Gaussian cylinder, take contribution of flux from each surface, curved surface and end faces. Curved surface will give you 0 contribution, and finally you will get the formula electric field as sigma upon 2 epsilon 0, where sigma is surface density of charge. And you will love to know here the electric field depends on R, where there the electric field don't depend on R, it is independent of R. So this is the second last charge assembly which we are going to see. And then we are going to come to the last assembly, charge assembly. Using Gauss's law, one can find the electric field. This particular charge assembly is charge shell. If you take a charge shell now, what is meant by charge shell? Hollow metallic shell having charge on it. So it will have surface charge density. Surface charge density sigma will be charge upon area. Surface area is 4 pi r square. If r is the radius of the charge shell, one can find the electric field outside the charge shell by taking the point P outside. You can define the what is called as element vector here ds bar. Find out the flux through this surface using the same concept of total electric flux. And then what is the charge enclosed by that? you can resort to the formula E is equal to sigma upon epsilon 0, capital R square upon small r square, where capital R is the radius of the charged spherical shell and small r is the distance from the center to the Gaussian surface. So Gaussian surface has a radius small r. There you can easily encounter using that particular formula. Now, if you choose that point P very close to the surface, then you will get the formula sigma upon epsilon 0. And if you choose a point P inside the spherical charged shell and construct a Gaussian surface in that Gaussian surface won't include any charge. That's the reason total flux will be 0, electric field inside will be 0. So if you start at the center of the charged shell, electric field is 0. As you proceed towards the surface, till surface is reached, the electric field will be 0, and then it becomes maximum value, that is sigma upon epsilon 0, and after that it goes on decreasing by that formula inversely proportional to r square. And this is the beautiful depiction of the graph where you can understand how exactly the electric field varies with the distance. So this is more or less the whole chapter of chapter 1, and we can understand the important concept behind this. These important concepts are very well done. One can go through the NCERT book and do it, and one can refer some other books also and understand. Now, all this, we can actually study more applications of this, more detailed physics in this. Electric field, magnetic field, we always encounter everyday life. The light which is coming from the sun is in terms of is the interaction of electric and magnetic field. Scattering which is taking place, how exactly the dipoles of the constituent air interacts, behaves when this interaction of electric and magnetic field takes place. That's a curious thing to study. That one can go in detail and try to study more physics behind this. So from all this, all discussion, I can tell you in the chapter in physics, you have plenty of diagrams, plenty of derivations. Learn the derivation. There are numericals involved. So that's the reason I define physics as is not only is a legal way or official way. It is defined as study of natural occurring phenomena. My definition of physics is physics consisting of beautiful diagram, handsome derivation, gorgeous concept, awesome explanation, and mind-blowing problems. Thank you.
Prudent Scholars, powered by Lupin Pharmaceuticals.